Okay, welcome to the second video on lipids, chapter 17. The first video we covered sections 1 and 2. Here we are, section 17.3. In the first video we talked about fatty acids and prostaglandins. And so now we will be talking about fats, waxes, and oils. Waxes and triacylglycerides. These are the two things that we'll be talking about in this. So really just talking about waxes and triacylglycerides, or glycerols rather, also called triglycerides. Now, these in green here, there's a reason these are highlighted in green. These in green are referred to as saponifiable. And we'll talk more about a saponification reaction in a little bit, but if you remember the chapter on carboxylic acids, we talked about esters, and we talked about saponification of esters. That's the base hydrolysis. So saponifiable lipid saponification is the base hydrolysis of esters. So the fact that I'm saying these are saponifiable lipids basically means that they have an ester. And we'll look at that functional group in just a moment. Okay, waxes. What we're talking about here, right? There's beeswax, carnauba wax, jojoba wax. You could also put in here, put it up here, earwax. Right. So what these waxes are is essentially we've got a long chain. This is 14 CH2, so 1 plus 14 is 15, 16 carbons long. It's an acid, so here's the acid group. Let me use red for acid. Right, so here's the acid, 16 carbon long acid, C16 acid. And then it's esterified to a 30 carbon alcohol. So I'll use blue for the alcohol. We have a C30 alcohol. The ester is this functional group right here. Right. So waxes are esters of a saturated fatty acid, here 16 carbon acid, and a long chain alcohol, 30 carbon long alcohol. So the ester linkage, if you remember, is a combination of an acid, and I'll just put here, there's the tail of the alcohol, or tail of the acid, and then the alcohol, right? Normally the alcohol would be, put it here, HO, and then 30 carbons long, real long here. So what we have here is this alcohol portion here. So it's very, very hydrophobic. Very hydrophobic. One of the things we talked about in lecture about esters, alcohols at least 5 carbons or less are soluble. Acids that are 5 carbons or less are soluble. Alcohols that are 5 carbons or less are soluble, but you put the two together, of course now it's 10 carbons long, it's bigger, but this ester linkage does not provide, even though there's a couple oxygens here, it does not provide much polarity. So these are very hydrophobic, not soluble in water. And primarily, if you look at their uses in nature, well, except for beeswax, where they're actually used to make the structural component for the honeycomb, leaves have a waxy coating. Your earwax also performs a protective role. So actually, I'll put it up here. So performs a protective role. Fats and oils, triacylglycerols, or again, we can call these triglycerides. So when you, if you get blood work done and they check your cholesterol, they might also check your triglycerides. That's the same thing, these triacylglycerols. So fats and oils, remember fats, these are solids at room temperature. Oils are liquids, but they're both lipids. just depending on the melting points. Lipids have a lower melting point. They're liquids. Solids have a higher melting point. Fats have a higher melting point. They're solids. So higher melting point. And what these guys are esters of glycerol. And glycerol, probably, well, you might remember this. Glycerol is a 3-carbon alcohol, so 3 carbons, but it's got an alcohol group on each carbon. So it's 1,2,3 propane triol. That's glycerol. And so what we're going to do here, if this is, think of this as a scaffolding or a backbone, we're going to hang 3, right? Tri means 3. We're going to hang 3 fatty acids, or esterify 3 fatty acids to each one of these alcohols. All right, so here we go. Here's glycerol, the propane triol, 3 carbons, alcohol in each carbon. And what we're going to do is stick a fatty acid on here, stick a fatty acid here, stick a fatty acid here, so you get glycerol. And then the reason it's acyl, this ACY, there should be actually an L there. They missed the L. Try AC, acyl. This acyl, that is just like another name for an ester, essentially. This ester group is like an acyl group. So we have simply fatty acid 1, fatty acid 2, fatty acid 3, esterified to glycerol. We have a triacyl glycerol. So in cartoon form, right, we have the glycerol backbone, 3 fatty acids, and again, these are ester bonds. Esters can be saponified, so this is saponifiable. Right? So what that means is we could cook this up with some sodium hydroxide, and we would get the glycerol back, plus, will we get the fatty acids back? Well, kinda. I'll say here 3 fatty acids. But remember, sodium hydroxide is a base. So this is base hydrolysis, is saponification. Hydrolysis. What happens to a fatty acid when it's in a base? An acid plus, okay, so again, glycerol, 3 alcohol groups, 3 fatty acids. It's esterified. And by the way, this is done in cells by enzymes called esterases. These are enzymes that link these 2 together, or I should say 4 together, link these fatty acids to the glycerol backbone. All right, so they're just saying here olive oil contains a high percentage of oleic acid, which is monounsaturated, so it puts these kinks in the molecule. Remember we had those kinky oils. So if it puts kinks in the molecule, it's going to have a lower melting point, and it'll be a liquid at room temperature. Now again, oils are going to be liquids at room temperature. They're talking here about olive oil. Well, olives come from plants. Right? I mentioned earlier we talked about vegetable oil. We don't talk about vegetable fat, we talk about vegetable oil. Right? So vegetable oil or corn oil come from plants, and they are liquids. Right? Here all they're saying, again, a fat is going to be a solid at room temperature. Fats are solids. But the thing about this is these guys come from animals. Meats, well, milk, butter, and cheese. These come from animals. Right, so we talk about animal fat, whereas oils come from plants. So we talk about vegetable oils, animal fats, vegetable oils. And a lot of this, again, really has to do with the fact that these guys are saturated. So saturated fats, unsaturated fats. These have the double bonds in them, those kinks in the molecule. Okay, of course, here we're talking about esterifying the acid group to glycerol, but still it's this kink in the molecule that lowers the melting point. This is, again, just saying the same thing. They have cis double bonds, which puts kinks in the molecule. They can't pack together tightly, so the van der Waals forces is minimized. They have low melting points, and they're liquids at room temperature. So here again, in a space filling model, they're just showing how these chains don't line up. You don't get good interaction between these chains, and so you don't have the close packing, and the melting points are lower. This is interesting. We're looking at the melting points. Now these, maybe you want to just focus on the saturated. So the saturated is in blue here, right? The other two have either mono or polyunsaturated, but the saturated, right? So beef, butter, these are high in saturated fats. Clear by this graph. Coconut oil, I don't have palm oil on here, but coconut oil, this is one of those tropical oils that I mentioned. Now, they call it coconut oil, but look at the melting point. The melting point is actually very close to room temperature. Okay? So 25 degrees is just a little bit above normal room temperature. So a hot day in the kitchen, in the summertime, this is not going to be a solid but a liquid. And then in wintertime, when it gets colder in the kitchen, this is going to be a solid. But look how much saturated fat is in coconut oil. And the reason this is important is because diets that are high in saturated fat, lead to increased blood cholesterol. So, your doctor, maybe not for you if you're not an old guy like me, but your doctor might be interested in what your blood cholesterol level is, and that's because it's predictive of heart disease. So people who have higher blood cholesterol have atherosclerosis, hardening of the arteries. They can get atherosclerotic plaques or blockages in their arteries from this cholesterol, and it leads to a heart attack and stroke. So I'll just say heart attack, or maybe I should have said myocardial infarction, attack, stroke, death, right? So you don't want to have a whole diet with a lot of these saturated fats in them, because it leads to higher blood cholesterol. Instead, you want, if you're going to have lipids in your diet, you want them to come from plant oil that's high in polyunsaturated fats. Remember, the omega-6 and omega-3 are actually cardioprotective. Right, so this slide is talking about something interesting. Hydrogenation. I'm not going to really, we'll talk about hydrolysis in a bit, but we'll talk about hydrogenation here first. Remember, hydrogenation, if you have a carbon-carbon double bond, and we'll make it a cis double bond. Okay, we'll make it a fatty acid. So it's an unsaturated fat, right? You can react this with hydrogen. It says a nickel. This is a nickel or platinum catalyst. I don't really care a whole lot about the catalyst. The main thing is you're adding hydrogen across that double bond, and you go from an unsaturated fat to a saturated fat. Okay. So when you hydrogenate one of these unsaturated fats, you go from something that's relatively healthy to something that is unhealthy. So when you look on food labels and stuff, it might say partially hydrogenated. So what does partially hydrogenated mean? Partially hydrogenated. I won't get into the details here, but you can do this reaction, and I'll put platinum here, and then you heat it up. If you don't have enough hydrogen, so you're not saturating, you're not putting hydrogen across all these double bonds, instead of we're going to start with this unsaturated fat here. Instead of actually hydrogenating it, so I'm not going to put hydrogen there, but I'll just put platinum, and the triangle means we heat it. You go from an unsaturated fat, it's still unsaturated, but now it is one of these trans fats. So it's a trans unsaturated fat. And you might be familiar with the fact that these trans fats are even more unhealthy. So I'll put here very unhealthy. So what's happening here is that because you're not adding the hydrogen, it's isomerizing. So we get it, we'll put here cis, right? This is cis. We go from cis to trans. This is an isomerization. And it turns out, for reasons I won't get into, the trans form is favored. So this reaction is really kind of an equilibrium, but the trans form is favored, it's more stable. And so, in fact, you don't even need to use platinum or something. If you just heat up one of these vegetable oils in a pan, you get it too hot, it can actually isomerize and form trans fat. So you want to be careful that you don't heat these oils up too high in a pan. And they talk about different smoke points and whatnot. Some oils are better at handling that than others. But the main thing I want you to understand is that unsaturated, cis double bonds, good, healthy. Saturated or trans unsaturated with the trans double bond, unhealthy. These have higher melting points. They're solids at room temperature. This is a liquid at room temperature, lower melting point. So they're not saying anything new here. Adding hydrogen across that double bond converts the double bond to a single bond, or we could say, or isomerizes from cis to trans, increases melting point, and decreases. What does it decrease? The healthiness. Products such as margarine or shortening, these are partially hydrogenated vegetable oil, right? So tub margarine, solid stick margarine, not good for you. A better thing to do is instead of using this stuff, what you can do is, because butter, it is saturated, but it doesn't have these trans fats. These guys have trans fats in them because it's partial hydrogenation. If you add butter plus oil, well, these are both hydrophobic. So what you can get is just these products that have butter that is mixed with oil to make it kind of a spreadable. A spreadable, I'm going to say a spreadable butter. But they've lowered the melting point by adding oil to the butter, so it's actually healthier for you. Soft margarine is nice because, yeah, it's spreadable, but it's got these trans fats, so it's not good for you. Trans fats, right? These are formed during hydrogenation. It's isomerization. The cis is converted to trans. In the body, they behave like saturated fats, increase blood cholesterol. Studies reported to raise cholesterol. LDL cholesterol is maybe I should write this down. This is what they refer to as the bad cholesterol, and HDL is considered the good cholesterol. And so these trans fats, actually, they've been outlawed in some parts of the country where they're not allowed to be used in restaurants and consumer food goods. So it raises the bad cholesterol and lowers the good cholesterol, and you want to avoid these things. All right, learning check. You might want to read this over and then pause it, and then see how well you do. Are there more unsaturated fats in vegetable oils? I think what they're saying is, are there more unsaturated versus saturated? I'm going to guess that's what they mean. Versus saturated, question mark. Yes, that's true. There are more unsaturated fats, so that's true. Vegetable oils have higher melting points than fats. No, that's not true. That's false. Fats have higher melting point. So we'll put it here. False. Hydrogenation of oil converts some cis double bonds to trans double bonds. Yeah, that's that isomerization reaction, right? The partial hydrogenation, where the molecule reacts with the catalyst, but there's not enough hydrogen there, so it just converts to the more stable trans form, which is really bad for you. Animals' fats have more saturated fats. Yes, that's also true. Hydrolysis can be done in one of two ways. Here we're talking about the acid hydrolysis, so acid or enzyme catalyzed hydrolysis. So with acid hydrolysis, again, you're going to add water across these esters and break these ester linkages. You're going to get glycerol back, the alcohol. Right, alcohol's in an OL, so this is the alcohol, and then 3 fatty acids. Now notice this is done under acidic conditions, so the acid here is going to be protonated. Let me just we'll make acetic acid here real quick acid, right? If you put acid into water, it ionizes. We get the carboxylate ion. So here, plus hydrogen down here, plus the hydrogen ion. So this is the free acid. It's called the free acid. It is protonated or unionized. That's what we have here. So if we add, remember the Chatelier's principle and buffers and all that, if this is under acidic conditions, we have a lot of hydrogens here that shoves a hydrogen onto the carboxylate. Remember, this is called the carboxylate. If the acetate ion, the carboxylate ion, gets protonated by the hydrogens here under acid hydrolysis, and it shoves the equilibrium back to the free acid, the protonated form or the unionized form. So that's the first way. The second way is base hydrolysis, also known as saponification. Saponification, this is the base hydrolysis, reaction of a fat with a base. So saponification is base hydrolysis, and is also soap formation. So saponification, actually, you can just rearrange these letters a little bit. SOAP. This is soap making. So before COVID interrupted our semester, we were going to do a lab where we made soap, and the same exact, well, pretty much the same reaction happens. You're going to take the triglyceride, right? This triacylglycerol, and it splits it into the glycerol and 3 fatty acids, right? 3 fatty acids, but because it's under basic conditions, we get the salt of the fatty acid. Okay, so what is a soap? This saponification is a soap forming reaction. Soaps are salts of fatty acids. Now, if it's a sodium salt, right? How can I do this? Let me write it this way. So we have the long chain, squiggly, OO minus. And if it's sodium, this would be a solid or a bar soap. If it's potassium hydroxide, right, you get the potassium salt, like sodium salt, potassium salt. This would be a liquid soap. So here they show the reaction. We have the glycerol backbone. Let me use blue for that. Here's the glycerol backbone. We have the 3 fatty acids. Fatty acid 1, fatty acid 2, fatty acid 3. You cook this up with sodium hydroxide. Oh, this is also, by the way, this is also known as lye. So lye soap is simply soap that was used sodium hydroxide. And you get the glycerol back. Right, this is just free glycerol. It's not esterified anymore. It's just free glycerol. and they put the stoichiometry in here, plus 3 fatty acids that are the salt, the sodium salt of that fatty acid. So this is the sodium salt of the fatty acids. Okay, lastly, soap or detergent. We know what soaps are. Soaps, right, these are salts, either the sodium salt if it's a bar soap, or the potassium salt if it's a liquid soap. These are salts of fatty acids, right? They're derived from the base hydrolysis of a triacyl glycerol, G-L-Y, glycerol, right? So saponification. That's what a soap is. What's a detergent? They're not the same thing. Down here we have a detergent. Notice this functional group, this, let me just, well, you can see it here, C double bond O dash O minus. We have something similar, but it's sulfur. Sulfur, right? Sulfur double bonded to these oxygens, right? And we have this long hydrophobic tail. We'll talk about how soaps work later, but right now I just want you to notice the similarities, right? We have a sodium salt, right? A sodium salt and a long hydrophobic tail. Like, was it 14, 15 carbons? This is actually what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This goes by the name of sodium lauryl sulfate. It is the sodium salt of a sulfate. The lauryl means there's 12 carbons. Another name for this is sodium dodecyl sulfate. Dodecyl also means 12. And this is usually abbreviated SDS, so SDS for sodium dodecyl sulfate. It's the same thing as sodium lauryl sulfate, and you find these in detergents. So detergents have it's a sodium salt of a sulfonic acid. Sodium salt of a sulfonic acid. Soaps are sodium salts of fatty acids. Well, what's the big deal? Again, if we were able to do that soap lab, what you would have been able to see is that these guys, there's something called a hard water reaction. If you have a divalent cation like calcium ions, calcium plus 2, or magnesium plus 2, these guys will form an insoluble salt. You'll still get, here, let me do, I'll put it here, magnesium plus 2, and then we're going to have, COO, right, COO minus, and the long chain here, and then another one. So 2 of these, right, 2 negative charges balance the plus 2 charge. This is insoluble. It does not dissolve in water, whereas soap clearly does, right? Soap, you mix it, your bar of soap keeps getting smaller and smaller and smaller because you're using it up. It mixes with the water, it lathers up, whatnot, it dissolves. This forms an insoluble precipitate with calcium or magnesium ions, and it's what we call soap scum. So if you have hard water at home, that tackiness, that kind of sticky, filmy stuff that you feel on your skin, right? That's because of this soap scum that's formed. Okay? Detergents don't do this. If we were to react this, and I mentioned it, but I didn't write it down, hard water. Hard water contains calcium ions or magnesium ions or both. This stays in solution, so it stays soluble. In other words, no soap scum. So detergents work better in hard water conditions, whereas soaps don't. And in addition to the obvious chemical differences, the physical difference here is that detergents don't have that hard water reaction. They stay in solution, whereas soaps will react with hard water to form soap scum, these insoluble precipitates.